All right, great. So I want to start today with the clarification of some of the things that we've done involving primes and irreducibles. Specifically, I want to just explain something that was glossed over in a lot of the previous lectures, specifically that prime element and irreducible element are not synonyms. This is an important point. So, can anybody tell me what a prime element is? Yes?
If P is able to divide, first of all, P is not 0.
Yeah.
And,
well, actually, it could be 0.
Oh, really?
Yeah.
Okay.
But it's not something else. It's not a unit, exactly.
And if it divides the product of two numbers, then it divides one or the other.
Exactly. So the definition is prime element P means P is not a unit, and P divides AB implies P divides A or P divides B. Exactly. What's an irreducible element? Yeah, sure. Go ahead.
An irreducible element is not equal to 0. I'm pretty sure that. Am I right so far? Because I know what.
It'll follow, but I mean, the thing is, yeah, go on.
All right, if there's no proper divisors, so if it is only divisible by a unit, and something of its only divisor is a unit.
Exactly. So here's a definition. R is not a unit. And if I have a factorization of the thing into some product here, AB, then either A is a unit or B is a unit. This would, of course, be false if this thing were 0, because I could always have these sort of factorizations, 0 times something else. So that the fact that it's not 0 is implied by this. So, of course, there is a relationship always in any domain. So let's just let R be a domain, which, recall, means that there are no 0 divisors. In other words, if AB equals 0, then A is 0 or B equals 0. In that case, we do know some sort of relationship. What do we know? What's the relationship in an arbitrary domain between a prime and an irreducible? Exactly. Any prime is irreducible, at least any non-zero prime. So if P not equal to 0 is prime, then P is irreducible. Does everybody know why this is? Anybody who doesn't know the proof of this, put up their hand. So okay. So you haven't seen the proof of this?
I may have, but
okay.
Maybe if you were on this.
Right. So, well, I mean, you start off with something, obviously, which, you want to prove that something is irreducible. So you want to, look at a factorization and show that one of these things must be a unit. Well, if I have a factorization like this, then in particular, P divides AB, which is good because, we can then sort of use the fact that this thing is a prime to show that either P divides A or P divides B. Now, without loss of generality, we can say that P divides A. And so we write, say, P equals CA. But we know that P equals AB. So we have, A equals PC, rather. A equals PC. And so we rewrite this as P equals AB equals PCB, because we have this way of rewriting A. Now, one of the major points, of course, is that this is a domain, right? We needed that as a hypothesis. So this means 1 minus CB equals 0. And since P is not 0 by hypothesis, this implies 1 minus CB equals 0. That's the definition of domain in our hypothesis. So C is an inverse for B. So B is a unit. So we've shown that P must be irreducible. Okay, so here's the big problem. The converse is false for an arbitrary domain. Can anybody give me an example? We saw a very nice example last class. Go ahead.
2 times 3 equals 1 plus radical minus 5 over
Yeah,
minus 1.
exactly. Or in the sort of more general format we gave last time. So I mean, I'm going to give you exactly the same example, but I'm going to do it for arbitrary d non-square, or square-free rather, less than -1, congruent to 3 mod 4. So here's the thing. Last class, we saw that if we look at z join square root d, where d is square-free, in other words, any prime, any rational, any standard, usual integer prime dividing d only can divide it once. D is less than -1, d congruent to 3 mod 4. We saw we had this lovely factorization. 2 times 1 minus d over 2 equals 1 minus root d, 1 plus root d. And we showed that 2 is irreducible. We proved this. But 2 is not prime, follows from this formula. Why?
It doesn't divide either of the factors.
Exactly. 2 divides 1 minus root d, 1 plus root d, but we also pointed out that 2 doesn't divide 1 plus root d, and it doesn't divide 1 minus root d. So 2 is irreducible, but 2 is not prime in this particular ring. So the major point here is that you should watch out and not make errors on problem sets or exams. Yes?
What is a good way to show that something's irreducible? Because it seems as if you'd have, how would you even go about that?
You need to know something about the structure of a ring. So, I mean, in this case, to show irreducibility, you needed to know a little something about what it looks like if you're in an imaginary quadratic ring. You had to use various hypotheses and various structural results we accumulated. There's really not much else I can say. There's no sort of general technique for deciding when something is irreducible in a particular ring. You have to just use whatever structural results you have. So I just want to quickly run through a review also to sort of maybe clarify a few definitions which we're sort of given ambiguously. I want to also go through some of the special rings. That we've talked about so far. And we had this sort of filtration of rings. So we had like all rings, and then we looked at a subclass of all rings, which we called domains or integral domains, but I'll just abbreviate to domains because it's shorter. And the point here is, of course, there are no zero divisors. But the really essential thing about there being no zero divisors is that you have a cancellation law. This is the thing that you sort of use most, that you have this cancellation law. I mean, I've written it that way over there. I've sort of written it out longhand, but the point is that if I have A not equal to 0 and AB equals AC, then in a domain, I know that B equals C, even though I don't have an inverse for A. So that's just a sort of main way that you use a domain. But domains don't have a huge amount of structure, so you often pass to a more restricted class. And we called them domains with unique factorization. I'll call them unique factorization domains because that's the usual name. And there was a bit of an ambiguity issue in the way we talked about unique factorization, because we talked about it as if unique just meant up to reordering. There's also the point, of course, that it's unique up to associates. So, primes are somehow not uniquely defined. They come in a class of associates. I mean, you often think of primes as being the same element if they are associate to each other. What does being associate mean? Sorry? Exactly. So things are associate if they differ by a unit factor. So unique factorization, unique means up to reordering of factorization and up to associates. Is that clear? And then we looked at PIDs, principal ideal domains. These are subclass of the unique factorization domains. So these are the rings where these are the domains where you know that if you have an ideal, then it must be generated by some element, by some unique element. Sorry, not unique, by some element. Then we had a subclass of that, the Euclidean domains. Where you had a division algorithm. Now, there was a bit of a sort of nomenclature issue here. We called the division algorithm a Euclidean algorithm. I mean, in some sense, the name Euclidean algorithm more properly applies to the method for calculating the GCD given the division algorithm. And I think there was an exercise where you were supposed to actually come up with the Euclidean algorithm based on a division algorithm. But you call the thing a Euclidean domain because you have both this division algorithm and a Euclidean algorithm. Is that pretty clear to everyone? Okay. So, I mean, and remember, the point is that you do have this sort of this thing we called maybe a Euclidean norm or something, which is distinct in general from the notion of norm that we introduced last time. This is just some sort of general size function. And, of course, the idea was, and here's a hypothesis that was left out, if you start out with some element, the one that you're going to divide by is not 0, then you can write so for all a, b, such that b is not equal to 0, there exists a quotient and a remainder such that a equals b cubed plus r, and r equals 0, or delta of r is less than delta of b. And there are various ways of normalizing the Euclidean norm and so on, but that's really not that important. So for instance, yeah, it is quite possible, for instance, that in one of the sorts of rings that we were talking about in class, these like z adjoins square root d, that the notion of norm that we introduced last class, where you multiply a plus b root d by a minus b root d and get a squared plus b squared d, is not going to give you a Euclidean norm, but that there is nonetheless a Euclidean norm on that ring. This is a distinct possibility. There's nothing to rule that out. And going the other way, of course, it is utterly, utterly, utterly false that just because you have this norm that it in any way tells you that there is a Euclidean norm. I mean, there's absolutely no sense in which that's true. So that's an important sort of distinction. We have these sorts of common terms running around, but they mean different things in different contexts, so beware. Then what would be like sort of the smallest thing that I might put here? Something that's automatically a Euclidean domain by a sort of trivial norm. A field. So this sort of relates all of the different sorts of rings that we've talked about so far. Fields are, the sort of smallest, most restricted class. And in some sense, the main thing about this sort of sweep is that there's an increasing complexity as you pass in this direction from fields to all rings in terms of two things, the ideal structure and the structure of the group of units. So as you pass this way, you get more and more ideals and much more complicated ideal lattice structure, and you get much more complicated rings, groups of units. And a lot of what you do in ring theory is you try to explore the structure of the lattice of ideals and the structure of the ring of units, because you can relate that to a lot of sort of basic, number theoretic problems and a lot of other sort of algebraic problems. There are all these sorts of areas of math which rely specifically on knowing those things. So you need this sort of structural theory. Now, I'm going to make some abbreviations. I'm usually going to refer to things like unique factorization domains as UFDs, principal ideal domains as PIDs. I might even abbreviate Euclidean domains to EDs. Now, why do I do this? Not to confuse you, but because this is standard in the literature. If you ever read a paper, you're not going to read principal ideal domain. You will read PID because nobody wants to write it all out. Okay. Actually, I'm going to move back over here. So I just want to do very, very quickly something where we look at examples of each of these things which is not an example of the previous. So for instance, an example of a ring which is not a domain is Z cross Z. Someone give me an example of a domain which is not a UFD. We saw them last class. Yeah? We're generated by something, right, exactly. So Z joins square root D, where D is square free less than negative minus 1 and congruent to 3 mod 4. So this is not a UFD. We showed that last class, and we showed it again over here. Okay, so what's a UFD which is not a PID? You've seen lots of examples of this.
Like polynomial?
Exactly. So for instance, we saw that if you have a unique factorization domain, then the polynomial ring of that UFD must be still a UFD. So for instance, Z join X is a UFD, but nonetheless it's not a PID because it has ideals like X comma 2, which are certainly not principal. Another option would be a field to join two variables, and you consider the ideal generated by those two variables. So PID, which is not a Euclidean domain. Now this one's hard. I'm just going to give it to you. There's no way that you could really be expected to see this offhand. There's a sort of nice theory that explains why this is a principal ideal domain, but not a Euclidean domain. But Z adjoin 1 plus square root minus 19 over 2. Example of Euclidean domain, which is not a field. Well, that's easy. Z, say, and fields, well, consider the real numbers. Great. Okay. So now an addendum. So the sort of first note I made is that if R is a UFD, and I have some R and R which is not equal to 0, then under this very important hypothesis that I'm working in a UFD, and we've seen that there are a lot of things which are not UFDs, a lot of very nice things which are not UFDs, for instance these. But if R is a UFD, then R is irreducible if and only if it's prime. Now, we've shown this in one direction. The other direction is easy because you just consider the unique factorizations, and you know that R is irreducible, so it must divide the other side. It must divide, must be in the unique factorizations of the things on the other side, so you get that the thing must in fact be prime. That's the essential point. That because you know how you have this unique factorization into irreducibles. Remember, this is UFD means factorization up to associates of irreducibles. You have this, and that's why we often make this sort of confusion. So in UFDs, we sometimes interchange prime and irreducible. But don't misapply this. For instance, when you're talking on an exam about Z join square root D satisfying these hypotheses, don't make the mistake of saying that something is prime if and only if it's irreducible. Okay, so now I want to talk about sort of the way of taking this notion of prime and bringing it to the world of ideals. another way of sort of seeing what I'm about to talk about is it's a sort of broader class than maximal ideals. It encompasses maximal ideals, but it gives a lot more things in much the same way that a field is a domain, but the converse is false. And we'll see exactly how that can be made precise. So I'm going to talk about prime and maximal, which I abbreviate maximal ideals. So recall that if I have a proper ideal in a ring, then we call the thing maximal if and only if any ideal stuck between this ideal and the entire ring must be either that ideal or the entire ring. So there's nothing sort of properly stuck between. Now, what was our sort of clever way of characterizing maximal ideals in terms of quotients of a ring?
They're fields.
Exactly. So here's the theorem. M is a maximal ideal if and only if R mod M is a field. And this is because we understand the structure of the ideals of a quotient. If we knew the lattice of ideals in a particular ring, then we could figure out the lattice of ideals in any quotient of it. And we know that fields are characterized by their having these two ideals, the zero ideal and the full ideal, the unit ideal, and them being distinct. So that's how we saw that. But now I want to sort of broaden that class. So here's how I'm going to do that. So definition. Again, suppose I have some proper ideal of R. This thing is called prime ideal. If whenever I have some product of elements in P, then I know that one of those elements is in P. Now, why is this somehow a generalization of the notion of prime element? Well, it shouldn't be hard to see that P is a prime element if and only if the principal ideal generated by that element is a prime ideal. So what's the main reason that's true? The main reason that's true is that the statement that P divides something is the same as saying that that element is in the ideal generated by that thing. So the definitions just sort of become, clearly equivalent. In other words, P divides AB implies P divides A, or P divides B can be translated under this into just saying that AB is in this ideal generated by P implies A is in the ideal generated by P, or B is in the ideal generated by P. Is that clear? Any questions about this? Okay. Now, do I have any reason to think that if I have a prime ideal in general, then it must be generated as the principal ideal by some prime element? Absolutely not. In fact, it's absolutely false that in general, a prime ideal is going to be generated by some prime element. So don't make this mistake. So these are distinct ideas. So can anybody give me a nice example of a prime ideal which is not principal? So P prime does not imply P equals P for some prime element P. Exactly. One of the easiest ways of getting something like this is by looking at a polynomial ideal. So for instance, note that z join xy modulo the ideal generated by xy is isomorphic to z. Well, I will show in a minute that this implies that this must be a prime ideal. Here's an easier, I'm going to show in a minute that prime ideals are characterized by the fact that their quotients are domains. So just accept that fact for a minute. This implies then that the ideal generated by xy must be a prime ideal, but xy is not a principal ideal. We've seen this in various forms previously. So let me actually prove that backup statement that primes are characterized by their quotients. So this thing is prime, but not principal. But in order to completely justify this, we need the following result, that P is prime if and only if R mod P is a domain. So this is sort of a statement, of course, analogous to the proposition you had over here that maximal is characterized by the quotient being a field. And this is pretty obvious. Does anybody want to go through the proof of this? Okay, sure. So I'll go through a proof of this. So going in one direction, suppose I have xy equals 0. So I'm going to assume that P is prime, and I'm going to try to show this thing as a domain. So I'm going to say that suppose I have some, these things. Let's make sure that they aren't zero divisors. Well, I can lift these things, this x to some x tilde, and this y to some y tilde in R. So these are just preimages under the canonical homomorphism from R to R mod P. And we know that by definition of this canonical map, x tilde y tilde must be in the kernel, namely in P. So we have x tilde and y tilde, lifts of x and y, and the fact that the multiple of x and y is 0 says that these things are in this prime ideal. Now, by hypothesis, this implies, since P is prime, that x tilde is in P or y tilde is in P. But that's just saying that x equals 0 or y equals 0 because, again, of the definition of quotient. Is that clear? The other direction is identical. You just reverse the argument. You just sort of start out with these things and then you take the descents rather than taking lifts. So this is a very easy result. It's a very nice characterization, and one of the best ways of thinking in general about domains about prime ideals is that they have quotients being domains. Now, what's a sort of immediate corollary of this? And we know that every field is a domain, right? Because we can take these. Because we can, if we had some xy equal to 0 in a field, then we could always just multiply by in inverse unless, one of the things is 0. So what does that tell us about the relationship between maximal and prime ideals? Exactly. So a corollary, an immediate corollary of this is that if M is maximal, then M is prime. And the proof is, of course, just that R mod M being a field implies that R mod M is a domain. This is by far the easiest way of proving that a maximal ideal is prime. Here's another sort of corollary. What's a way of characterizing domains in terms of the ideal structure of the ring? So, is there an ideal which is prime if and only if that ring is a domain? Well, the zero ideal, because R modulo the zero ideal is just R. So R is a domain, for instance. R is a domain if and only if 0 is prime. And the proof of that is that R is R mod 0. So this thing is a domain. In other words, R is a domain if and only if 0 is prime. So this is another nice sort of characterization of the relationship between domains and things like primes. Okay. Excellent. So we've talked about a sort of string of special ideals, and they had this nice sort of filtered form. We had these, most general things, all rings, and then descending all the way down to fields. Now I want to talk about something which doesn't quite fit into that filtration. It's sort of something parallel to that filtration, and it's not described explicitly in Artin, which is a pity because a lot of what's going on in Artin in sections 11.10 and thereabouts are really sort of, they seem like these weird sort of disjointed results which have nothing to do with ring theory in general. In fact, they're very much at the heart. The arguments there are very much at the heart of what's going on in ring theory. But the reason for that is never mentioned. So I'm going to, in an extremely simplified form, explain the underlying theory behind what's happening there. And I think that this is useful because I think otherwise it's very difficult to remember what's going on. It just seems like a bunch of random things about quadratic fields. But these are not random things about quadratic fields. They're actually very general and deep and important results. And they are about these things called Dedekind domains. Now, there are very complicated definitions of Dedekind domains, but there's also an extremely simple definition of Dedekind domain, which is usually omitted from most textbooks, and for a very good reason, because by the time you usually get to Dedekind domains, you've built up a whole bunch of extra theory. But you don't need it. The only piece of theory that I need to introduce is the notion of multiplication of ideals. So if I have some ideals I and j in R, then I define their product to be what? Can anybody tell me what the product of two ideals is?
Settable sum, finite sums where A times B, where A is I and B is B.
Exactly. It's the set of all finite sums of AI, BI, where the AIs are in I and the BIs are in J. You need the finite sums, of course, because you need this thing to be an ideal. You want to define the product of ideals to be some ideal. If you just had products, then you wouldn't necessarily know that, for something which is not, for instance, generated by a single element. For if I or J were not principal, you would not know that the thing would be closed under addition. So you need to have these finite sums to make sure that the things are actually a subgroup. Now, and it's very easy to verify this is an ideal. I mean, it's certainly a subgroup because you have these sums and so on. And it's closed under multiplication by R by the fact that I and J were individually so. Now, just to make sure that we're all on the same page, if I do have two principal ideals, say A and B, so this is I and this is J, then what is the product IJ? So in this extremely simple case, what is the multiple of the ideal generated by A and the ideal generated by B? Exactly, the ideal generated by AB. So at least when you have principal ideals, this is the simplest possible operation. It's just multiplication of elements. Is that pretty clear? Any questions about this? Okay, good. So, as I promised, here's another type of special ring. So suppose we have our domain with field of fractions K, and assume that that field of fractions is not the initial ring. Put another way, we have a domain which is not a field. Then we say R is a Dedekind domain if for every ideal there's a sort of other ideal which when you multiply by this ideal gives you a principal ideal. This is the key definition. And it's mirrored in the book in these propositions about how you can multiply an ideal by its conjugate to get a principal ideal. But this is the correct sort of generalization. And it makes it much clearer what the salient information is. All the results there you can prove without working in a quadratic field, but just with the sort of assumption that I'm going to write down. So for all ideals, there exists another ideal such that their product is principal. So I multiply these things, and this thing is principal. And I'm going to assume, of course, that this J is not equal to the zero ideal. Otherwise, I'd have this trivially true. So if there's some non-zero ideal such that this thing is principal. So here's an example which is worked out in the book, and I highly recommend that you work out why it's true, because it gives you an idea of what happens in greater generality. So suppose I start out with Q join root D, where D is square free, some square free integer. So I'm going to use a slightly different notation because it's actually the general notation used in the literature. In the book, the letter R is used for the ring of integers in a quadratic field. In general, the notation is O sub k. The reason for the O is that there's this terminology of order. I'm not going to explain this right now, but the idea is that OK is this sort of something called the maximal order in K. But suffice it to say that that's a synonym for the ring of all algebraic integers in K. And we know what the structure of this is. So what is it? Exactly. So if D is congruent to 2 or 3 mod 4, it's just Z adjoins square root D, exactly. And if D is congruent to 1 mod 4, exactly. So we know exactly what this thing is. And this thing is a Dedekind domain. Remember, to prove something is a Dedekind domain, you need to show that for every ideal, you can multiply it by some other ideal, some other ideal, and that product had better be principal. That's your hypothesis. This is what you need to show. And this is shown in the book in the guise of Artin's proposition. I think this is 10.8.10. Proposition 10.8.10. Because what proposition 10.8.10 says is that if I is an ideal of this OK, this thing OK, an ideal of OK, then I think that Artin uses the notation bar. To be consistent with Professor Gross, I'm going to use the notation prime. So I'm going to consider the set of all alpha primes, A minus B root D, as alpha being written in the form A plus B root D ranges over I. Now, in the case of some quadratic imaginary field, this is really just complex conjugation. And in general, the term you use is conjugate. This is the conjugate of alpha. So if somebody talks about the conjugate, they often mean the complex conjugate in the case of something that embeds in the complex numbers in this way. But in general, just this A minus B root D as the image of A plus B root D. Is that pretty clear? Any questions? Am I going too fast? All right. So this is an ideal satisfying the product of I and I prime is the principal ideal generated by n, where n is not just some element of OK, but is in fact in Z. So this is proved. This is a lovely little result, and I'm not going to go through the proof now. It was in the assigned reading. But this in particular shows that this thing is a Dedekind domain. So that's fabulous. Is that pretty clear? So the fact is that this is actually a very general result. In fact, if you have any field which contains Q and which is of finite dimension over Q, then that thing is, in fact, if you consider the set of algebraic integers in that field, then that thing is, first of all, a ring. But secondly, and more importantly, it's actually a Dedekind domain. So just the general fact is this generalizes to K field that contains Q and such that the dimension over Q of K is finite. So you define, again, OK equals algebraic integers in K. And the point is this thing is, first of all, a ring, but more importantly, it's a Dedekind domain. And this is an important theorem. But for now, we're satisfied with just dealing with Q adjoined square root D. What's the dimension of Q adjoined square root D over Q? 2. The dimension is 2 because you have everything being of the form A plus B square root D. So you have these two parameters, these two Q rational, these rational parameters, A and B. Or put another way, you have a basis 1 and square root D over Q. Okay, so here's a sort of useful result on the structure of ideals in a Dedekind domain. So the whole point of Dedekind domains is somehow that although you don't necessarily have unique factorization, so these things are not in general UFDs, you have no sort of way of fitting this nicely into the filtration that we talked about before. So you don't necessarily have this nice factorization into irreducibles. But you do have a sort of a substitute, which is in some ways just as good. So here's what the substitute is. And it's a it works out as a really, really great substitute. So let's assume that I have a Dedekind domain. So DED-DOM, it's just an abbreviation. And suppose I have some non-zero ideal in that Dedekind domain. So the theorem is that I can be written uniquely. So there's some unique way of writing an ideal. You can't necessarily write elements in some sort of nice, unique way, but at least you can get at the ideals in a nice way. So I can be written uniquely as I equals P1 through PK, where PI are non-zero primes, prime ideals. So I have these prime ideals. I can talk about the prime ideals of R, and what this result says is that tells me everything about the ideal structure of this ring, because every ideal can be written uniquely up to reordering. But here it's just legitimately up to reordering. There's no additional caveat. There are no associates or anything like that. All of the theory of associates and so on is built directly into the ideal structures. I mean, so there's no need to worry about anything other than reordering. So anything can be written uniquely as a product of these primes. This is a very, very nice result. So, for instance, if you wanted to prove that something was principal, if you wanted to prove that a Dedekind domain, suppose you already knew that something was a Dedekind domain, and you want to show it was a principal ideal domain, for instance, it would suffice to consider the prime ideals, because you know that every ideal is a product of the prime ideals. So you just have to show that the prime ideals are principal, and that would show that every ideal is principal. This is a very nice sort of result. It sort of gets at, I guess, somehow one of the reasons that these things are important. Yeah, absolutely.
How do you know that the product of the prime ideals is prime?
Oh, it's not. In general, the product.
I'm sorry.
If I had the every prime ideal were principal, then each of these things would look like little p1.
Right.
So by hypothesis, these things are all principal. So I can write these as little p1 up through little pk. And the product of these ideals, remember I mentioned before that A times B is AB.
Right.
Well, that would imply that, by induction, that this thing is just P1, PK. So this thing is a principal. Is that clear?
Yeah.
Okay. Okay, great. So as I said, this gives a way of salvaging unique factorization. So example, in z join square root minus 5, we have these two factorizations into irreducibles. So these are all irreducible. So we don't have unique factorization into irreducibles. But by this result, which I'm erasing now, remember this thing is a Dedekind domain, so we do have unique factorization into prime ideals. And here is its unique factorization into prime ideals. 2 join 1 plus root 5, 2 join 1. If I'm leaving minuses off, then you can add them yourself. Times 3, 1 plus root minus 5, 3, 1 minus root minus 5. Okay? And this is a unique factorization. So this is unique. Unique factorization into prime ideals. The fact that each of these is a prime ideal is something that I won't go into, but suffice it to say that the quotient by this is z mod 2, quotient by this is z mod 2, quotient by this is z mod 3, quotient by this is z mod 3. Yes?
How did you generate that factorization?
That's in general hard, and it's sort of beyond the scope of this lecture, but there's a hint of how that's done in section 11.10. In fact, beyond a hint of it. I mean, it sort of actually goes through a way of mechanically doing this. But it's an algorithmic process. It's not one that's a priori interesting, but there is a sort of way of doing this. There is a systematic way of doing this. So the final thing I want to talk about in preparation for Monday's lecture is class groups. So these are these things that you can attach to Dedekind domains. And they're very, very useful because they sort of provide a response to the following result. So here's the result. R is a principal ideal domain. R is, if and only if, R is a unique factorization domain. So remember, unique factorization domain, and a Dedekind domain. Now, one of these directions is hard. Going from UFD and plus Dedekind domain to principal ideal domain requires a little work. I will not go through it. But there is one direction which is easy. Going from here to here is easy. Why is it easy? Can somebody give me a quick proof of the fact that if I have a principal ideal domain, then it's a UFD and a Dedekind domain? Yeah. Absolutely. So first step is that, yes, we already know that PIDs are automatically UFDs. So it suffices to show it's a Dedekind domain. And then? Well, remember, the definition of Dedekind domain was that for every I, we had to find some j such that this thing is principal, right? Well, exactly. So, I mean, exactly. I could just take the unit ideal. I just start out with any ideal. I already know it's principal. It's generated by some r. And I just multiply by the unit ideal, and that gives me something principal. So it's automatically true that for any ideal I have, there is something some non-zero ideal I can multiply by to get something principal. Is that clear? Okay, so I need to show that for every ideal, there is some second ideal. So for all I, there exists some j which is not 0, such that this thing is principal. So I start out with some ideal. I already know it's principal because I'm in a PID. By hypothesis, I have a PID. So this thing equals something generated by R to start with. Then I can multiply by, say, the unit ideal, and this thing is principal. Is that clear? Yeah. Good. Okay. So one direction is easy. The other direction relies on showing effectively that Dedekind domains have the beautiful property that they can be generated by two elements. They may not be principal, but they can be always generated by two elements. And from that, it's not that hard. I mean, once you can show that, then it's not that hard to show that unique factorization in addition implies that every ideal is principal. So some there's a sort of subclass of the Dedekind domains, and those are the principal ideal domains. And you might ask, is there some measure of how far a Dedekind domain is from being a principal ideal domain? So you have these principal ideal domains, you have these Dedekind domains, and there's a sort of question, how do those fit in? Like, how can you sort of almost quotient out, the set of all Dedekind domains by the set of principal ideal domains? And there's a sort of way of measuring that out, a way of sort of creating a stratification of Dedekind domains. And here's the way of doing that. So this is a new idea, and that is class groups. So this measures how far a Dedekind domain is from being a PID. Great. Okay. So to define a class group, or to define the class group of the Dedekind domain, to define the class group of the Dedekind domain R, then we define an equivalence relation. On the set of ideals. So we say that two ideals I and j are equivalent. This is our definition. This is the relation we define. They're equivalent if and only if there exist some elements of R such that Ri equals Sj. And these things are not 0. So R is not 0 and S is not 0. Otherwise, the thing would always be trivially true. All these things would be related. So the assumption is that there are some non-zero things which you can sort of cross-multiply to get an equality. And the fact that this is an equivalence relation and so on, you want to be able to use the fact that it's a Dedekind domain. This doesn't work in sort of general things. I mean, you really need to be sort of working with something like, say, these quadratic rings. So we're going to let angle brackets I denote the equivalence class of I. We call this the ideal class of I. So angle brackets I is the ideal class of I. It's the equivalence class under this relation. And then what we do is we define as a set the set of all ideal classes. I just want to make one note here. I exclude I and j from being the zero ideal. So I always forget in all of this about the zero ideal. So again, for I not equal to 0, we define this equivalence class. So this is a set of all ideal classes, or put another way, this is a set of all angle bracket i's as I ranges over non-zero ideals. And here, again, is a use of the fact that we're working in a Dedekind domain. Proposition. If we define the multiple of the ideal class of I by the ideal class of j to be the ideal class of the product. So remember, we defined multiplication I ideals, and that gave us an ideal. So it has this lovely ideal class and everything. So if we define the product this way, then so this defines, well defines. This is really well defined. In other words, if we choose a different representative for I and so on, everything works out. Yeah. So this is a C, CLR, class group of R. It's the same notation as in the book. I'm using Artin's notation, even though it's a little non-standard. So this well defines a group structure on CLR, the class group of R. And the basic point is that, so here's another sort of quick result, and this is easy to prove. Easy proposition. So if I have a Dedekind domain, then R is a PID if and only if the class group of R is trivial. Is the trivial group. So remember, this thing is a group. We just gave it a group structure. So this thing is some group. So I mean, it's not empty because I have the class of the unit ideal, for instance. And what this says is that the only class is the class of the unit ideal. And why is that true? Well, it's just sort of by definition. Well, here's one of the directions. I mean, suppose we go from PID to this result. Well, the idea is that I know that I can write any ideals I have as, A and B, and then I know that BI equals AJ. So that means that I and J are related under the equivalence relation, so I and J are in the same class. So any two ideals are in the same class. And the other direction is just as easy. And one last sort of remark, I realize it's getting late, but one sort of last remark is that whenever I have, say, one of these rings of quadratic integers, or more generally the ring of algebraic integers in some larger field, then the class group is finite. So there are two last sort of themes here. Class groups are finite. And I'll just give you an example of that to finish this off. So if I consider the class group of the set of algebraic integers in Q join root minus 5, this thing looks like it consists of the class of the unit ideal and the class of the ideal generated by 2, 1 plus root minus 5, and is isomorphic, of course, therefore, to Z mod 2Z. The point being that if I square the ideal 2, 1 plus root minus 5, then I get a principal ideal. But it itself is not principal. And more generally, to calculate these things, so to calculate the class group of O, Q join root D, where D is negative, look at section 11.10. That's the reading for Monday. This is worked out. There's an algorithm for finding the class group, which is worked out.